so this is the experiment for the thin lens equation, okay, the virtual experiment now. And basically what we want to do is find the relationship between the object distance, okay, the object distance as shown here, okay, and the image distance. Okay, of course, the confusing thing about this particular one is how to position the object, number one, and number two is how to position the ruler lah. Okay, so if you've already done this, and your reading is a little bit different than mine, don't worry about this lah. Okay, but actually what we can get from the graph is more important, the shape of the graph and also the relationship from the graph. That one is actually more important lah. This is how I would do it lah. Okay, although the reading that we're going to see actually is from one of you lah, but this is how I would do it lah. So let's say I want to position it at 50, so I would actually put the 50, and I will put it along this line over here. So let's say this is 50. Okay, and what I will do is I will adjust this until the beginning of the pencil touches the 0. This is how I would measure the 50, because that's where the light comes from, the top of this pencil lah. This is how I will measure the 50 lah. Then after that, how I would measure so this is the object distance. So the image distance I will take from the starting of this one all the way until the pencil over here. So actually my reading is around 9. Well, I guess if I start from here, it's about 190 lah. My image distance. Okay, because I go from point to point. Okay, but I understand. Okay, I understand that when I was giving a briefing the other day, it seemed a bit very kabo-kabo lah, kan. Saya main letak saja itu pencil, kan. But this is probably no fault in your part. Okay, maybe I forgot to mention this lah. Okay, that actually I wanted it from the pencil because that's where the light comes from, and then you measure from where the light goes to. I believe that actually if you use this method, you will have a more accurate answer. But actually either way, even if you're consistently doing the entire thing wrong, your relationship should still be correct. Okay, which is what we want to discuss today lah. Okay, so if you want to redo this after today's class, you're free to do this. But you probably have to find another graph paper to draw your graph on lah. Okay, so let's go to our final subtopic, which is the thin lens formula. Okay, and in this thin lens formula, we have looked at we have looked at this one. Sorry, this one actually should be 40, correct? Okay, so this is the inference, the hypothesis, the aim, manipulated variables are all here. Okay, our hypothesis is when the object distance increases, the image distance decreases. And this is actually the relationship that we want to study in this subtopic. Okay, the relationship between U and V. Okay, the object distance and the image distance. And we find that this relationship is actually sort of inversely proportional. Okay, when U increases, V will decrease. Okay, and this is our setup. We started with 100, and then we went to different image distances, object distances, 90, 80, all the way to 50. Okay, in real life, this is actually how the setup will look like. Okay, you have an object over here. In this case, it's a candle. In our lab, usually we use a light bulb. Okay, and then we adjust the position of the screen until you get a sharp image form. Yes, it's going to be terbalik because we know that most of the images are, read, rim. Okay, all inverted. So definitely going to be terbalik. Okay, and actually from the simulation that you saw just now is also terbalik lah. Okay, now this is one set of readings that I got from one of your classmates lah. Okay, it may not be correct or it may not be the same as yours. Okay, but doesn't matter. The only question you need to answer is the reading consistent with our hypothesis? Our hypothesis says that when the object distance increases, okay, the image distance decreases. Okay, or the other way around lah. When the object distance decreases, the image distance increases. Is it consistent? Yes, it is. It is consistent, and I think that is more important than getting the right value. Okay, when we do experiments in general, it is the pattern and the relationship that we are more interested in, rather than what is the correct value. What is the correct value? That was mathematics. Okay, when we are looking at physics, we are looking actually more at the relationship. Is the relationship consistent with our hypothesis? Okay, so I wouldn't really sweat so much over these values. Most importantly is that kamu kira dengan betul lah. If you have the V66, make sure your answer is about 0.015, and so on and so forth. The relationship is actually more important than the value. Okay, and when you draw the graph, okay, the same rules of graph apply. No matter whether your value is as tiny as 0.01 or 0.005 or as big as 0.02, your graph needs to be a big size. So you always have to adjust your scale, okay, so that you get a graph that is roughly around this size. Okay, if your graph is only sini saja di bawah sini kan, obviously that's not the right graph lah, bahkan. You have to adjust the scale, zoom out, zoom in to the scale to get a bigger scale so that your reading, your graph size is always big. So when you draw the graph, you should get a graph of this. Okay, please ignore this straight blue line here. You should get a graph something like this. Okay, you should extend it all the way until you get an intercept, okay, and a y-intercept. Okay, and we're going to use this graph today to talk about two important things lah. Okay, number one, in your own graph, I want you to determine the y-intercept. Okay, and then of course, after that, give me the gradient. Okay, calculate the gradient. The normal way we always calculate gradient. Okay, determine 2 points, draw the triangle, and calculate the gradient. Okay, so I'm going to give you maybe about 2 minutes to do this. Okay, determine the graph. Sorry, determine the y-intercept, and then after that, find the gradient. Okay, the intercept is 0.017. Okay, don't forget the unit for the intercept is the same as the y unit, so centimeter minus 1. What scale should we use for the x-axis? Well, if your values are pretty similar to mine, the x-axis is this one, right? 1 over u. Perhaps 2 cm to 0.05 lah. Perhaps. Okay, like 2 cm, okay, to 0.05. No, 0.005. Okay, so you get like here 0.005, 0.010, 5, 10, 15, 20 lah, 0.015, 0.020. Yeah, I know the x-axis is a little bit funky lah, because it's almost the same length or width as the 1 over v, but your space is going to be pretty small because there's no, I can't think of any other scale because if you're going to use 1, 2, 5, or 10, if we use 2, it can't fit because you have to go all the way to 20. So I guess 5 is the next best option lah. Okay, and then alternatively, your y-axis over here, since at least for mine, the smallest value is 5, possibly I can use 0.002, 2, 4, 6, 8, 10, all the way until, I'll get somewhere up here lah. Okay, 0.016, my biggest value. Okay, so that, when you draw the graph, you get something like that lah. Okay, so yeah, I hope that helps. Sorry, gradient is -1. Okay, so yes, the gradient over here is -1. Okay, so if your answer is around this value, everybody else, okay, if your answer is around this value, I don't think it will be much of an issue. Okay, once again, it is the pattern that matters, and we want to learn something from this y-axis, okay, which we're going to talk about in a little while. Okay, I'm just going to skip to the last part first, the precautions. So the precautions for this question is do the experiment in a dark room. Okay, and the reason why we are doing this is to get a more accurate reading. Okay, or to get a sharper image, to get a more accurate, sharp image. Okay, this can also be a precaution, because if you do it in a bright room, the brightness of the surroundings may affect your sharp reading. But of course, we're doing this virtually, so it's a different story altogether. Okay, those of you who've played with the lenses before, you know that actually doing the experiment in a dark room is easier for you to determine the actual image distance that gives you the sharpest image. Okay, within a bright room, the surrounding light is a little bit too bright, lah. Okay, and a little bit disturbing. Okay, so now it all depends on what your answer is for here, lah. Okay, my original answer is this one. So let's do the number 3. Deduce how you would use the value of the intercepts to relate to the focal length of the lens. So this is a very important thing that we need to remember, is that the y-intercept, okay, the y-intercept is the value of 1 over f, okay, 1 over f. So in Faith's case just now, this is my example, okay. When I did the reading, I got the answer 0.1. My y-intercept over here, so dapat 0.1. But in Faith got 0.017. Okay, fine. So let's use 0.017. Let's cut this out. Okay, so we use C equals to 0.017. This is again Faith's reading, everybody. Okay, now if C is 0.017, most important thing is that we need to know that 1 over F is 0.017. So what is my F? Okay, F will be 1 over 0.017. Okay, 0.017, which will give you about 58.8. At least this is my answer lah. Okay, 58.82 cm. Okay. Now, of course, the question is, in the experiment that we did, the value of the focal length is actually 40 cm. Kan? That's the value of the the focal length that we did in the experiment. Okay, but in my calculation over here, I got the value of 58.82. Again, okay, again, we're using this graph just to learn something. Okay, yes, it's going to be different because there's all these things that, that actually in, even though we did it virtually, the way you measure is different. Okay, maybe you measure it using my method, you measure it using your own method. So this will probably all, lend to the fact that why you didn't get 40 lah. Of course, if any one of you got 40, then you're very good lah. Okay, chun 40 lah. Okay, so that's congrats to you. But the most important thing that we need to take away from this, okay, is that when we draw a graph of 1 over v against 1 over u, the y-intercept represents 1 over focal length. So we can find the focal length, the graphical, from the graph, we can find the focal length from the graph of the lens, okay, by using the y-intercept. And this is the method to do it. Okay, if you're confused about, oh, what is Sir talking about this, just take this away from this one. When we draw the graph 1 over v, 1 over u, the y-intercept represents 1 over f. So you can find f. Okay, just kasih terbalik sajalah 1 bahagi 0.017. Now, number 4, write down an equation to relate between the object distance u, the image distance v, and the focal length of the lens. Okay, now let me explain to you how this works. So if we follow y equals to mx plus c, okay, sorry, let me change to my laser pen. Okay, if we follow y equals to mx plus c, which is the general equation for a straight line, okay, and my y axis is 1 over v. Okay, so it's 1 over v. My m, okay, so my m is the gradient. Remember just now what is the gradient that you got from here? -1 bahkan. Okay, so if Faith got -1, if the rest of you got a different value, doesn't matter, replace that value in here. This is an example only, my example, okay, which is -1. Okay, and then the c is the x-axis is 1 over u from the graph. Okay, and finally, the 1 over f, okay, sorry, this 1 over f over here is 0.017 in Faith's case lah. So actually, this should be written something like 1 over v equals to -1 over u plus 0.017. Okay, this is how Faith's graph would look. the equation will look like this. -1 because of the gradient, and then 0.017 is the y-intercept. Okay, this is how the equation will look like. Okay, but theoretically, this is how we get the thin lens equation. 1 over f equals to 1 over u plus 1 over v. Okay, because when I bring this across, it becomes plus. So 1 over f equals to 1 over u plus 1 over v. And this one, okay, is what we call the thin lens equation. Okay, the thin lens formula is 1 over f equals to 1 over u plus 1 over v. It has its roots in this particular graph. That's why I asked you to draw this graph first. Because from this graph, we can determine that, oh, okay, this value over here is 1 over the focal length. And from there, we can determine the equation, which is 1 over f equals to 1 over u plus 1 over v. Okay. Number 5, state the relationship between the object distance and the image distance. I believe that this is not in your handout. So, oh, it is. It's number 4. Okay, it is number 4 in your handout over here. Okay, so number 4. Okay, number 4 in your handout, state the relationship. Of course, the relationship is V is inversely proportional to U. Okay, I would actually suggest or recommend writing linearly decreasing, because that's what our shape of the graph is. It is a linearly decreasing graph. It is a straight line that is one get bigger, the other one becomes smaller.
Sorry to disturb, but if it's linearly decreasing, so it has to be 1 over v.
Oh, yes, correct. I know. So I know. Yeah. So thank you very much. 1 over v is linearly decreasing with 1 over u. Okay, but if it is just v and u, you're right. Thank you very much. V is inversely proportional to u. Okay. Oh dear, my writing is all over the place. But yeah, roughly there lah. Okay. If it's linearly decreasing, then 1 over v is linearly decreasing with 1 over u. Okay. I believe that you have 3 lines over there, so you can write both the relationships lah. 1 over v is linearly decreasing with 1 over u, because that's what our graph tells us. But if you really want to write u and v, then make sure you write v is inversely proportional to u. Okay, don't just write inversely proportional, because our graph is actually not an inversely proportional graph. Okay, our graph is 1 over v against 1 over u. So according to the graph, 1 over v linearly decreasing 1 over u, or v is inversely proportional to u. Let's move on. Okay, so to sum up, okay, this is our relationship for any real image, which is the Ritz rim. Okay, for any image that is real, okay, when u increases, v will decrease and the image becomes smaller. Okay, when you make it further and further away from the lens, okay, the image will become smaller. And the distance between the image and the lens will also become smaller. Okay, in short, u is inversely proportional to v. The object distance is inversely proportional to the image distance. And the object distance is also inversely proportional to the size of the image. When you put the object nearer, the size of the image gets bigger. Okay, so I guess you can copy this down somewhere. Any empty space that you have. Okay, because after this, we're going to do the calculation questions. Okay, let's continue. So now we come to the main event okay, the second main event, which is the thin lens formula. Okay, now the thin lens formula is pretty easy to use. You don't have to. There's no need for you to change the unit if every unit is the same. U is the object distance, V is the image distance, F is the focal length. If all three are, say for example, if all three are in cm, there's no need for you to change the units. Just make sure that all three are in cm. Or if all three is in meters, then make sure it's all in meters. Not a problem. The one thing that you have to be very careful of is the situation in which you have to use the formula. Okay, so I would actually ignore the U part okay, because the U part is a little bit strange. Okay, so I wouldn't worry so much about this. I would want you to worry more about the V and the F. Okay, and this has to be remembered. Okay, if the V is a positive value, if you get lepas kau kira-kirakan and then your V is a positive value, it tells you something, that the image is a real image. Okay, if the V is a negative value, it tells you that it's a virtual image. And likewise, you also have to remember that if we are using a convex lens in this situation, then the f must be a positive value. Okay, manakala, if you're using a concave lens, then the f must be negative value. So this is something that I really want to emphasize, that you need to remember this, because sometimes you will have to know when is it negative, when is it positive. Okay, it depends on the question itself lah. Okay, let's take a look at the first question. Okay, an object is placed 30 centimeters from a convex lens. Okay, so we see that there's this word over here, okay, called a convex lens. And we saw just now, if we're using a convex lens, f is positive. Okay, so we are safe. Okay, so focal length of 20 cm, so the f is 1 over f is 1 over positive 20. No need to put negative lah. Okay, now the object is 30 cm. This of course refers to u. Okay, u is 30, f is positive 20. So you can use the equation lah, 1 over f. Okay, 1 over f equals to 1 over u plus 1 over v. Okay, and when you substitute it, you will get 1 over 20 equals to 1 over 30 plus 1 over v. Okay, flip it over and you get 60 cm again. Okay, if you don't know how to get this, let me just show it to you. 1 over v equals to 1 over 20 minus 1 over 30. Okay, this will give you, you get 1 over 60. 1 over v equals to 1 over 60. So how do I get the 60? Kasih terbalik sajalah. Okay, v over 1 equals to 60 over 1. Over 1 tak payahlah kan, bahagi 1. So v equals to 60. Okay, so the act of flipping over is something that I hope will not be a problem for all of you, but that's how you would do it lah. Okay, so then the question then is, how much is the magnification produced by the lens? Okay, so magnification is v over u. M equals to v over u. After you've calculated the v, you have the u, which is 30 cm. Okay, then you can get the magnification, which is 2. Okay, and there's no unit for magnification lah. Well, I guess even you put the word times also can lah. 2 times magnification also can, but not necessary. Okay, and finally, what are the characteristics of the image? Okay, of course, if in this picture you know lah, okay, it will be, since the magnification is more than 1, then it will be magnified. Okay, it will be magnified, it will always be inverted, and it will always be real. The only thing that you need to know is whether it is magnified, diminished, or same size. Okay, so if it is magnified, okay, you can put a note here somewhere, like if the magnified means the magnification is more than 1. Okay, that is magnified. If the magnification is equals to 1, it is the same size. If the magnification is less than 1, it is the diminished image. Okay, but in our case over here, since we are only interested in the real images, it will always be real and inverted. We're not talking about the virtual image yet. Okay, yet. Okay, let's go to the second question. Okay, an object is placed 10 cm from a convex lens. Okay, so once again, when we see the word convex lens, then we need to remember, oh, okay, the f is a positive value. Okay, u is 10 lah. So how far from the lens is the image? You get the same thing, do the calculation, and you should get v equals to negative 20. Correct. Even when you do the calculation, you will be able to get a negative 20. Okay, and as I said before, what happens if the v is a negative number? If the v is a negative number, your image is virtual. Okay, so, and that's why this value is important. In this case, just now, the v is positive. Okay, you know that it's real. Okay, but in this case, the image is virtual. Okay, when you calculate the magnification, however, no need to use the negative lah. Okay, the image distance is 20, object distance is 10. So 20 divided by 10 will give you 2 times. 2 means that it will be bigger. Okay, as we said just now, if the m is bigger than 1, then it will be a magnified image. So what is our characteristic? It will be, since v is negative, it will be virtual. Okay, and if it is a virtual image, you know from the read, raise, rim, boom, boom. Okay, virtual means automatically it's upright and automatically it's magnified. Just to double check, the magnification is bigger than 2. Okay, which is why I emphasize so much itu read, risk, ring, boom, boom. Because in a convex lens and concave mirror situation, the moment it is real, it is always inverted. The moment it is virtual, it is always upright. If you cannot remember this, then it's very difficult for the characteristics of the image. Magnified, then you, sorry, yeah, the magnified part is you need to see the magnification, lah, whether it is more than 1, equals to 1, or less than 1. Okay, so everything that we have studied now actually comes together over here. Okay, and this question is not difficult actually. Okay, in terms of calculation, it's a pretty easy calculation. It is just that you have to remember a lot of things, which are, there's no reference book for you in the exam, so you have to remember this. Okay, the next question. An object is placed 30 centimeter from a concave lens. So we are in a slightly different situation. Just now was convex lens, and we said that convex lens, the F is positive. But since we're using a concave lens, the F has to be negative. Okay, so bear this in mind. This 20 cm over here is actually a negative 20 F. Okay, object is always 30 centimeters, doesn't really matter. Okay, let's calculate the V. How far from the lens is the image? Okay, I'm gonna let you do this first. Let me give you 1 minute to do. Try to calculate. Remember, the F is a negative value. Okay, try to calculate the V. So if you substituted everything correctly, you get negative 1 over 20. 1 over negative 20, also the same thing, doesn't matter. Equals to 1 over 30 plus 1 over V. Switch it around, you will get V equals to 12, negative 12 cm. Okay. Now I really hope that, sorry, I'm not to say I don't have time, but I don't want to waste so much time by explaining again and again how you get this V equals to this. Okay, so please figure out the math for this. I think that is a responsibility that you need to shoulder on your own. Okay, and it is very basic maths. Okay, how to get this V equals to negative 12. Now, what magnification? Remember, magnification is always V over U. Doesn't matter whether it is bigger or smaller. It is always V over U. Our V is 12, our U is 30. So our magnification, we will get 12 divided by 30, which is actually less than 1. Lah. Okay, 12 divided by 30 is 0.4. Okay, so this is 0.4 over here. Okay, and because it is magnified, the magnification is smaller than 1. Remember this? Smaller than 1 means it is diminished. So it is virtual because the object distance is negative, and virtual automatically comes with upright. Okay, so virtual upright, and since the magnification is smaller than 1, it will be diminished. Number 4, concave lens, concave, okay, with a focal length of 25 cm, forms a virtual image. Okay, the image is virtual, so remember V is negative. Okay, at a distance of 20 cm from the optical center of the lens. Okay, what is the original position of the end? Original position refers to U. Okay, so let's put down all the information. You want to find U. Okay, now our focal length is F. Okay, but remember, concave lens is F is negative. Okay, the virtual image at a distance of 20 cm, this refers to our V. Okay, but because it is a virtual image, it is a negative virtual image. Okay, so again, use the same formula, 1 over F equals to 1 over U plus 1 over V. Make sure you substitute the V and the F correctly. Try to find the value of the U. Most important thing is the answer should be positive, because the object distance usually generates positive. You're having a real object, like you're not having a virtual object. So where is the original position? If you substituted everything correctly, 25 is negative, 20 also negative, you get 1 over U equals to negative 1 over 25 plus 1 over 20, which you give it 0.01. Flip over the 0.01, you will get U equals to 10 cm. Okay, you should get this answer. Okay, question B. Draw the ray diagram to show the formation of the virtual image of the ant. Okay, I know there's not enough space. So virtual image is, and this is a concave lens. Okay, concave lens image is always virtual upright diminished. Okay, so you can just simply draw a normal one, kind of like this. Okay, draw the principal axis, draw the concave lens this way. Okay, remember that the concave lens looks like this. Okay, so if this helps, the line also this one. Okay, put the focal length somewhere over there, put the object near to the lens. Okay, so the object is over here, then the same straight two lines, okay, parallel and then diverge out, focusing on F. The second one is through the center, and then we will form the image over here. Okay, so this is our final drawing. Okay, last question. Oh no, I've given the answer away. Gosh, never mind. Okay, diagram 11.2 shows the formation of the image by convex lens. Everybody, convex lens is F is positive. The focal length is 6. The height of the object is 2. Okay, now you're given the image, the object distance over here 9. Okay, can you calculate the image distance? Go ahead, calculate the image distance. And then after that, I will explain this in a little while. Okay, calculate the image distance first. Okay, so if you've calculated, okay, actually from the drawing, so you know that it's a real image. So your V answer should be a positive answer. Okay, if you do everything correctly, you will get V equals to 18. Okay, 1 over V equals to 0.055. So you flip it around. 1 over 0.055, you get V, okay, which is around 18 cm. Now, how do you determine the height of the image? Okay, now in the past class, I told you that magnification, there are two ways to calculate the magnification. The first way is the one that we just talked about, which is the image distance over the object distance. But this value is also the same as the height of the image over the height of the object, high over whole. Okay, so that's what's happening over here. This is V, this is U, this is the height of the image. The height of the object is given in the question, 2 cm. Okay, this is HO. And that's how you get the height of the image is 4 cm. Okay, 4 cm high. Okay, so all in all to say that actually this particular subtopic, the calculation is actually not difficult. What is difficult is actually having to remember that, okay, if the focal length is like this, what does it mean? If the focal length is positive, the focal length is negative, what does it mean? When do you use positive and negative focal lengths? Okay, and then secondly, you also have to remember the image characteristic. Virtual image is, negative. Real image is positive. Once you remember this, you've done a few practices, I think this calculation is not really going to be much of a problem. Okay, and of course, finally, the magnification part. Remember that magnification, there are two ways to calculate it. The main way, yes, I know, is V over U. But you also have to remember that there's a secondary way, okay, which is the height of the image over the height of the object. And by calculating these two together, you can find one of the values as shown in this question.